Okay, hello everybody. The goals for today are to complete the discussion from last time, and then to talk about problems, a few problems that occur in knot theory. So, I mentioned that, well, okay, there is the obvious problem of separating knots, and invariant should be good for that. But I mentioned that I want invariants with good algebraic properties. I didn't yet say what that means. I will say at some point. But what do I need them for? I need them so that I can solve problems. So I'll have to introduce what problems occur in knot theory, or what are some of the basic problems that occur in knot theory. But let's first complete last class. So let me remind you, we spent much of the time, last time, showing that the Kaufman bracket is a morphism from the planar algebra of unoriented frame tangles. I forget what we called them last time, maybe T unoriented framed, I don't know. So it's a morphism from this planar algebra to the so-called temporally Lieb planar algebra, which we also define. In fact, most of the time we spent defining planar algebra, and then these two are actually simple examples. Then I still owe you why the rank of the temporally Lieb algebra is what is written here, and why this is good for computations. Okay? So first of all, what is rank? So rank is something that comes up in modules, in theory of modules. But you don't need to know. Basically, think the dimension like in a vector space, except it's not over a field, it's over a ring. So the number of generators that generated freely, if you can find generators that generated freely. Okay. Okay, so what's the dimension of temporally Lieb in 2n? So what's temporally Lieb? So temporally Lieb, 2n, I remind you, is, well, you take a circle with a base point, and you have 2n points marked other than the base point. So the connectors, the things that connect to the outside. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, say. And then you look for all ways of connecting, no, that's not going to work, all ways of connecting them in pairs with no intersections. So planar connections. So basically the dimension will be the and then you take linear combinations of these with coefficients in the ring. So the dimension will be the number of such, or the rank will be the number of such diagrams. So I claim that this number is the nth Catalan number, which is given by this formula, and which is, sorry, this is not equal, asymptotic, which is approximately equal, so asymptotic to this, or approximately equal to that, okay? How many of you have seen the Catalan numbers? Okay, so it's kind of outside of the material of this class. It's kind of basic combinatorics, which not too many people have seen. But it's such a lovely piece of basic combinatorics, and we can stay and root the whole time and not say hello to the pieces, not stop at vista points. Okay? So that's a vista point. Okay? So first of all, instead of writing it as a circle, let me write it as a line. So just cut it open at the base point. And then I still have 1, 2, 3, 4, 5, 6, 7, 8, an even number of endpoints, and I still connect them with arcs in such a way that there are no intersections. And now I want to count how many of such there is. So I claim that the number of such things, so you will take this set of such things, except instead of 8 have 2n in general, and I claim that the cardinality of this set is equal to the nth Catalan number, which is hereby defined to be, so by the way, the Catalan number, there is a paper by Richard Stanley in which he gives like 70 or 80 definitions of the Catalan numbers. So, and this is one of them. So to say that I define it to be something is silly because there are 80 definitions, and the whole point of the paper is to show that they're all equal. And by the way, there is a bit of that in knot theory. So I can probably give you about 40 different definitions of the Alexander polynomial. We'll get to about 2 of them in this class. But I could easily give you 40, and they're all equivalent. So what's the definition of the Alexander polynomial? I don't know. One of those 40. Anyway, here is another lovely definition which I like. So this is the number of histories of soccer matches. Soccer is European football, right? So is this how you spell soccer? Mm-hmm. So the histories of soccer matches that end with the score, that end with n, and in which team A, the first team, is never behind. Is never behind. So, you know, team A is always ahead. Maybe so 3-3 is a fair score because it's not behind, but it can be behind. You can't have 3-4. Okay? By the way, if I had dropped this condition, if I had dropped the last condition, so if I had dropped the condition that team A is never behind, what would be the number of histories? So when I mean histories, I meant how the score changed during the game. So basically, if there wasn't this condition, you'd have 2 n goals. N of them would be by team A. So you just have to choose which n. So it's 2n choose n. So, you know, rather than writing all of this, let me write it as an inequality. This is less than 2n choose n, or less than equal, because when n is small, it's actually equal. When n is 0, maybe. It's actually equal. Oh yeah, that's all. So why is this the same? It's the same because I can construct a bijection between histories and pairings like that. Namely, I will just look from left to right along the pairing, and every time I'll see a line going to the right, I'll call it a goal for A, and every time I'll see a line coming from the left, I'll call it a goal for B. Okay? So this is a goal for A. First goal is for A. So this is the score now is 1-0. This is again a goal for A, so the score is 2-0. This is a goal for B, so the score is 2-1. Then it's 2-2. Then it's 2-3. Sorry, what am I doing? Then it's a goal for A. So this is 3-2, 3-3, 4-3, 4-4. Okay? And and you can check its bijection. So whenever you have a history, okay, so first of all, in such a history, team A always leads because every line at the every closing line must have been opened. Okay, so basically every goal for B, whenever team B scores, it cancels against something that team A scored earlier. And you can check its bijection. You can check it on your own. So this actually gives us a very easy way of computing the Catalan numbers. Namely, let's draw it like this. So here is here is a table, and let's start this table with 0. So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and this is the score for team A. Yeah. So this is team A score, and this is, well, team B score. And what I want to put here, put in any box here. So in box ij, I will put the number of ways to get to this score. So the number of ways to get to the score ij in such a way so that team A is never behind. Okay? So basically, I've generalized the problem. Instead of getting to score NN, I'm trying to get to score IJ. So if J is greater than I, that can't be done, right? So basically, you have a 0 here, and a 0 here, and a 0 here, and a 0 here, and a 0 here. Also, you have, okay, the numbers I care about, the Catalan numbers, are the numbers below the zeros, the numbers on the diagonal. So let's compute them. How many ways is there to get to the score 0, 0? 1. How many ways are there to get to this score? To get to this score, the score, one goal before, must have been that one. So it must be one. Oh, there's only one way. How many ways to get to this score? So if you want to get to the score 1, 1, the score before must have been either 1, 0 or 0, 1. So it's either this or that. There are 0 ways to come from here, 1 way to come from here, so there's 1 way. How many ways to get to the score 2, 0? Well, that's still 1. How many ways to get to this score? So if I go to this score, I go to it either because team A scored or because team B scored. There is 1 way in which team A scored, so basically 2. So basically, every box is the sum of the one box to the below and one box to the left. So this is still 2. This is 1, 3. 2 plus 3 is 5. 5 plus 0 is 0. 1, 4. 4 plus 5 is 9. 5 plus 9 is 14. 14. So the Catalan numbers are 1, 2, 5, 14. I think the next one comes out to be 42, but, well, we can check. You can check. Okay, and if I'm wrong, who cares? it's kind of lovely to actually write the corresponding things, but not now. Okay, so how do I compute this? So this should remind you of the binomial coefficients. The binomial coefficients are obtained in exactly the same way. Okay? Except here I have the rule that there is a diagonal of zeros. Okay? So what do? So there is a clever trick, and I think it's called Andre's reflection principle. But I'm not sure I'm spelling it right. Okay? Anyway, the trick is the following. What I'll do is, well, I'll remove the indexes. Sorry, this just gets us confused. Or maybe I'll put them farther away. 0, 1, 2, 3. And I'll add a -1 here. And I'll add, so the indices go farther. So 0, 1, 2, 3, 4. And I'll just put zeros other than at this -1. Okay? And now the rule continue. And now I can use the rule both sides. Okay? So -1 plus 1 is 0. 0 plus -1 is -1. So I'll get -1 everywhere here. And then basically I'll get the reflection of the table below. Okay, so -2, -3, -4, -2, -5, -9, and so on. What have I achieved? Okay, so you see, but now instead of putting 1 and -1, I could put here A and B. And I'm only doing this to emphasize that here I'll have A plus B, here I'll have A, here I'll have B. So everything above is linear in A and B. But everything in the next diagonal is linear in the row before. So it's also linear in A and B. Everything in the next diagonal is linear in the previous. So basically every diagonal is linear in the previous one, which is linear in the previous one. So it's linear in A and B. So overall, this whole table is the sum of two tables. The tables in which you put 1 and 0, and the table in which you put -1 and 0. Okay? So the table in which you put 1 and 0, well, that's just the Pascal triangle. Right? That's exactly how you generate Pascal's triangle. So therefore, Cn is equal to, so now I want to know the entry up here in Pascal's triangle, and that's just, well, we actually computed here. It's 2n choose n. So Cn is 2n choose n minus the contribution you would get from the -1. The contribution you would get from the -1 is, well, if you think about it, you are in Pascal's triangle, instead of looking at the center element, you look at one element of the center. So this is 2n choose n minus 1. Okay? And then it's a matter of calculation. You put in the factorials, and you get, I hope, 1 over n plus 1, 2n choose n. I mean, that's just a stupid calculation. Are you with me? Am I wasting your time? Okay, good. Okay, and then the last bit is not interesting. So in other words, you know, there are formulas for n factorial, like n factorial is equal to, approximately equal to, what is it? 1 over 2 pi square root of n or n? N. Square root of n. I don't remember. Times n divided by e to the power n. Roughly this. No, maybe it's square root of 2 pi n. You know what? There are standard formulas for n factorial. You substitute them into the factorials that appear here, and you get the last one. Why do I care? Why does it matter? Okay? Sorry, are you still okay? Good. So why does it matter? It matters because what's our computational technique? If we have a complicated knot, so in fact, you may as well think of the GST48 knot, which is on your handout, which I will obviously not copy on the whiteboard because it's way too much work, but it's a some knot. So the width of a knot is defined to be, so you scan the knot from left to right. Well, you put it in the plane, you scan it from left to right, and or the width of a knot diagram. And at every point, you count how many strands do you cross. And of course, that depends on where you are. So here it's 4, and here it's 1, 2, 3, 4, 5, 6. Okay, so the width of the knot is the maximal, the width of a knot diagram is the maximal number of strands you cut with a vertical line. And in fact, the width of a knot is the minimum of all widths all of its diagrams have. But anyway, it's very hard to compute the width of GST48 because in principle you have to go through all of its diagrams. But it's very easy to compute the width of this particular diagram. So you just cut it with vertical lines and see how many crossings how many lines you cross. So I think here the crossing number is equal to 48. You can just count. But the width is equal to 12, I believe. The maximal width is 12. In general, you can expect that if the knot has crossing number n, the width will be approximately the square root of n, maybe twice the square root of n. Basically, think you have compare it with an array of size W by W of knotted stuff. So the width is W, but the number of crossings will be W squared. And that's actually a theorem, though it's a bit hard. So the width is always about square root the crossing number. Though it's very hard to actually compute it. To actually find the width is hard. Anyway, so how did our computation go? Or how did we compute? So we computed the Kaufman bracket up to a line. We got an element in the planar algebra corresponding to that many endpoints. So we got a linear combination of elements in TL4 here, in TL6 here, and so on. And then to go from one to the next, all you have to do is to add one crossing. Well, here I've added several. But, I mean, to go from one cutting line to the next, here, the next one will be this, all you have to do is to add one crossing. And if you add one crossing, you're really contracting with either this or with that. Right? Because the crossing becomes A times this plus B times that. Or maybe the other way around, okay? But anyway, you go over the element of TL4. For each one, if you add this, it either basically copies it, and if you add that, it closes one of the loops. But anyway, for each element, it's clear what it's easy to compute what connecting this or that does. So basically, the number of computations is the dimension of TL4. So the overall number of computations will be roughly TLW. Well, multiplied by n, because you needed to do this at most n times. Now, NTL of W is roughly n times, so now I have to copy the formula written there. So it's roughly n times whatever it was, something to the n to the 3/2 down here, with maybe a square root of pi, which really is, it doesn't matter, it's a constant. And then in the numerator, you'll have 4 to the power W over 2. Sorry, this is not n, this is W. So you'll need roughly that many operations. And W is square root of n. Sorry, why did I say W over 2? Oh, yeah, because yeah. So this is roughly n times, or some polynomials times 2 to the power W. So 2 to the power square root of n. And this is a lot less than 2 to the n, which was what we needed originally. So that's why we did so much better. Okay. Questions, comments? The estimates here are really, really rough, but I mean, I'm dropping polynomials, I'm dropping constants, but the exponential factors are right. So, okay. Good. So we actually already have one invariant and we can compute it reasonably well. But as I mentioned, we want to do more. So here are some problems we care about in knot theory. So problem number 1, the unknotting number. The unknotting number. So the unknotting number is the minimal number of crossings you have to flip to turn the knot into the unknot. So the minimal number of crossing changes to kill a knot K. So for example, if you look at the, what am I doing? If you look at the trefoil knot, then if you flip any one of the crossings, so let's flip this crossing, now it's the unknot, right? This pulls out and twists and it's the unknot. Okay, so the unknotting number of the trefoil, also known as the first knot with 3 crossings, is equal to 1. Can't be 0. Well, I mean, really by showing you that you can, that flipping one crossing returns it to the unknot, I've shown that the unknotting number is less than or equal to 1, but it can't be 0, because if it was 0, it would have been the unknot, and we can compute its Kaufman bracket and deduce that it's not the unknot. Okay. Okay, what's the unknotting number of a general knot? A related thing is the so-called Gordian distance. The Gordian distance. The naming is a bit funny. I mean, so I don't know if you know the story of the Gordian knot. So there was a town somewhere in what's now called Asia Minor, now called Turkey, called Gord something. And in that town there was a famous knot that was somehow knotted hundreds of years before by a guy Gord. I don't know. Okay. And then Alexander the Great, and there was some myth that whoever succeeds to untie that knot will become the ruler of the universe. And then Alexander the Great came there and tried a little bit and failed, and eventually used his sword and cut it and untied the knot. And indeed he became the ruler of the universe, which shows that the myth was true. So really, Alexander the Great computed or demonstrated that there is a finite distance between the knot that was that was there and the unknot. Okay, and then somehow the naming became the Gordian distance between two knots. So if you have K1 and K2, it's the number of the minimal number of flips to get from K1 to K2. Again, how do you compute that? How do you bound that? Can you prove that you need at least 3 flips to get from one complicated knot, take any knot in one of those pictures, to any one of the others? I don't know. Okay, so this is the first example. The second example is the genus of a knot. So I mentioned to you earlier that some knots are the boundary of surfaces. In fact, there is a theorem. So there is a theorem, probably by Seifert, because the resulting surface is called a Seifert surface. So a theorem by Seifert is that every knot in R3 is the boundary of a sigma G1, or of an embedded sigma G1, where what is sigma G1? Sigma G1 is the genus G surface. So sigma G1 is a genus G surface. Here is a surface of genus 3 with one boundary component put artificially. So you cut open and put here a circle. So, I mean, here I've shown to you that the unknot is the boundary of a genus G surface. But I could have embedded this surface in a more complicated way in R3, and then maybe the boundary itself would be knotted, and then it would be and then the knot would be the boundary of a sigma G1. Okay? Yeah. So the genus of a surface, so definition, sorry, the genus of a knot. So definition, the genus of a knot K is the minimum of G such that K is the boundary of an embedded sigma G1. So the minimum genus of a surface whose boundary is the knot. So in the handout that I gave you, the first 8 pictures are pictures of various 8 or 8 knots with surfaces whose boundaries are that knot. Now, there is a classification theorem of surfaces which says that every surface, every compact connected surface with one boundary component, every compact orientable surface with one boundary component is one of these sigma G1s. So even though it's not obvious that these surfaces are sigma G1, they are sigma G1. Okay. Should I give a class, maybe next class, explaining why all of these are really a sigma G1s, even if they don't look like it, and B, why is Seifert's theorem true? I mean, maybe I should, okay? But for now, I'm just introducing it as a problem. What's the minimal genus of a surface whose boundary is our knot? Okay. Next question. So maybe I should say about this one that it's to be continued. Even though it's a bit of an aside, it's not really, well, for the purposes of this class, it's just, you take it as a given. Okay. The next example. So, so this is an embedded surface. But I can also look at immersed surfaces. So surfaces that are allowed to self-intersect, provided the self-intersections are transverse. Okay? Claim every knot, so every knot is the boundary of an immersed disk. So disk is the stupidest surface of all. So it's really sigma 0, 1. A genus 0 surface with one boundary component. Proof, basically deform the knot to the unknot provided it's pretending that it can cross through itself. So just deform the curve to the unknot as a curve in R3 without worrying about self-intersections. And then continue deforming the unknot to a point. So the movie of this deformation is really a disk, right? So, I'm deforming the knot to the unknot, and this deformation, the parameter space is an annulus, and then I deform the remaining unknot to a point. So I close the annulus, and I get the parameter space is a disk. This disk may or may not be immersed in R3, But you can show that you can wiggle it a little bit, that generically it is immersed. Even if it has strange self-intersections, if you move it a bit, the self-intersections disappear. Sorry, the self-intersections remain, but they become transverse. So it's an immersed disk. But now an immersed disk, so an immersed disk is going to have self-intersections. By various theorems in differential geometry, which I hope you took, but if not, the intuition supports these theorems. So if you have two surfaces intersecting, and it's a transverse intersection, then so they intersect in a line. I don't know. If you have two surfaces intersecting, they intersect in a line. So if you have a disk self-intersecting in R3, it's going to intersect, you will be able to mark on it the lines on which it self-intersects. So there will be various lines on it which correspond to the to the intersections. And in fact, these lines are paired. So this is line number one. So in the parameter space, this line is, there is this line and this line, but in the target space, this line becomes the same as that line. And there could be other self-intersections. So there could be another pair, 2, 2, and another, these lines could touch the boundary, so there could be a pair 3, 3, and so on. Okay? Now, so these lines are just one-dimensional manifolds. Well, there are only two connected one-dimensional manifolds, and they can have boundary. So there are two connected one-dimensional manifolds. There is the circle and the interval. Okay, so basically you have all sorts. You have circles and intervals. Circles geometrically will look like this. So you have two pieces of surface and they intersect in a circle. Okay, you can see it. God, it reminds me of the most amazing riddle ever. But do I have time to tell you? I don't know if I have time to tell you, but I'll tell you anyway. So prove that if you have two potatoes, so what's a potato? A potato is kind of a sphere, a ball, a sphere, because I only care about the boundary. But with an irregular shape, it has bumps, and no two potatoes are the same. And let's pretend they're smooth. So prove that on any two potatoes, you have one potato and another one. Prove that you can mark a closed loop on this one and another closed loop on this one, such that the two loops are, what is it called? Identical. No. What's the word in geometry? Two shapes are isometric. Isometric, right. You can rotate and translate this so that it becomes that. Anyway, sorry. This is a hint. And what about the lines? So it turns out that there are two ways you can get an interval. And the two ways are a so-called clasp singularity, which locally looks like this. So you have two disks coming into each other, right? And they intersect in a line like this. So this is a so-called clasp singularity. And there is a second type, and it's the so-called ribbon singularity. So a ribbon singularity is a situation like this. So you have two bands, and they intersect like two bands intersect by a green line here. What's the difference between the two? So in the parameter space, so both of these bands are parts of the same disk. So in the parameter space here you have a disk, and this green line becomes two lines in the parameter space. One of which goes from a boundary point to a boundary point. This is as seen from the perspective of the vertical band. So one of them looks like this, and the other one goes from an interior point to an interior point. Right? This is as seen from the perspective of the horizontal disk. So in the parameter space, this is a pair of lines like this. Whereas a clasp singularity, again, the parameter space is a disk, and in the parameter space, from the perspective of the left part, this is a line of intersections that goes from an interior point to a boundary point. From the perspective of the right part, again, it's a line that goes from an interior point to a boundary point. So again, it's a line like this. And these two are paired. So, you know, if this is 1 and this is 1, then this would be 2 and 2. Okay? So in fact, the picture I drew here is wrong. I've paired 1 and 1 and 3 with 3, whereas the possibilities that really exist are to pair 3, so a thing like that with a thing like that, and so basically this is now a legal pairing. And there is yet another type, which is, so a line from the interior point to a boundary point can be paired with another such line. Whew. Okay, so claim these singularities you can always get rid of. So you can always find an immersion which has only clasp or ribbon singularities. So every knot is the boundary of a disk that has only clasp or ribbon singularities. And then definition, a knot is a so-called ribbon knot if it bounds an immersed disk with only ribbon singularities. And well, I'm out of time. I wish I had time to say more, and there is a little more to say, but so I will next time. But for now, let me just say that the next two pictures on the handout are pictures of ribbon knots. You can, so like the second one, the knot is in red, the disk is in blue, and the two intersections are in green, and you can see that they are ribbon intersections. And then a famous open problem is whether the GST48 is a ribbon knot. If it's not a ribbon knot, it will settle a famous conjecture. So, but we'll talk about it next time. Okay, see you on Friday.